So far, we have seen certain ring contraction and expansion rearrangements, especially in the case of interconversion of ring system. So first one was Demjanov rearrangement, and I think we already have seen Demjanov rearrangement in the previous class itself. So let me skip on that. Next one is Riffe-Matsky reaction. So Riffe-Matsky reaction is a synthetic method to produce beta hydroxy ester by treating a carbonyl compound such as aldehyde or ketone with an alpha haloester in presence of zinc and an inert solvent. The Riffe-Matsky reaction can also be conducted by taking propyl bromide or alpha haloamide instead of alpha haloesters. So the major reaction mechanism proceeds via the following steps. Here we can see the first step is the oxidative addition or insertion of zinc into the carbon halogen bond of alpha haloester. The main goal of the reagent or catalyst zinc is that it can make an enolate intermediate with this alpha haloester, which is named as zinc enolate, and later the zinc enolate ester can coordinate each other to form a dimer of the zinc itself, and then it will make a self-rearrangement which results in the expulsion of two zinc enolates, as you can see here. Then the oxygen of this ketone and aldehyde coordinates to the zinc, and another rearrangement or reaction will happen so that a carbon-carbon single bond will be created in the compound. And finally, after hydrolysis, a proton H plus or acid workup splits the zinc and oxygen to generate zinc, salt, and our product needed, which is beta hydroxy ester as the final product. There are many advantages with the Riffe-Matsky reaction. The first one is we can conduct this Riffe-Matsky reaction with the ketones having heavy substituents or bulky attached groups. Even if the ketone is heavily substituted, still the addition of nucleophiles to delta positive carbon of ketone is also possible. And another advantage is that if you want to conduct an intramolecular aldol reaction, you can choose Riffe-Matsky reaction because it's much easier in the case of Riffe-Matsky reaction. And another one is we have seen that there is a middle or intermediate compound like organo-zinc halide is formed in the middle of the reaction, and these type of reagents are pretty much stable, and we will get it commercially. And Riffe-Matsky reaction is found to be more convenient because the final product beta hydroxy ester isolation is very easy. And another merit with Riffe-Matsky reaction is we can use it as an alternative method in the case of aldehyde and ketone, especially with lithium enolate instead of zinc. And yield of this Riffe-Matsky reaction can be improved by using a freshly prepared zinc powder or copper zinc couple, etc. So these are some of the advantages with the Riffe-Matsky reaction. Next is olefin metathesis or alkene metathesis for the construction of macrocyclic ring compounds. So what is meant by metathesis? Metathesis means change in position. Okay, so alkene metathesis is also known as olefin metathesis, which is a reaction between two alkene molecules which results in the interchange of carbon atoms of their double bond. So as a result of this olefin metathesis, 2 sigma bond and 2 pi bonds are broken to form new 2 sigma bond and 2 pi bonds. So that is what olefin metathesis. Usually this olefin metathesis allows to exchange the substituents between two different olefins. Here you can see, suppose two olefins, M, which is attached with another substituent Y. Here this double bond is attached to the two substituents like R1 and probably this might be R2. And then after the olefin metathesis, you can see here the double bonds are broken and a cage-like structure or four-membered ring compound is formed. And then after the fragmentation reaction, what happened is this M is attached with the other substituent in the olefin MR1, and this portion is the other result or another product. So that is the result of olefin metathesis. So one of the benefit with this alkene metathesis is that you can exchange the substituents between two alkenes, or whatever be the alkenes reacted, they can exchange their substituents in between. So these type of reactions were used in petroleum reformation for the synthesis of higher olefins, especially the process is known as shell higher olefin process, which is conducted in presence of nickel catalyst under high pressure and high temperature. So in order to perform this olefin metathesis, there are different procedures available, especially ring closure metathesis, cross metathesis, and ring opening metathesis. So there are three different type of procedures and three different names. They are ring closure, cross metathesis, and ring opening metathesis. And I think as per your syllabus, you have to analyze what is ring closure metathesis, and we will come to that topic later on. So here in this example, when the molecule with the terminal vinyl groups are used, there will be an equilibrium developed by the removal of the product ethene from the reaction. Here you can see, if you are choosing two ethene group, and you will get a substituted olefins. And this olefin metathesis is somewhat like a cyclic process. Here you will see two olefins, two alkenes, especially two alkenes with attachments or substituents. They undergo olefin metathesis, and in the middle of that cycle, nearly the substituents are exchanged between these double bonds. Suppose this edge and this edge, this edge and this edge, they are combined together to form a cyclic compound, especially four-membered cyclic compound, and later it undergoes fragmentation. And then after fragmentation, here you have another alkene with the substituent groups are exchanged between these two alkenes. And then later again it proceeds with another rearrangement, like these double bonds are again broken down to complete the ring formation, and then again it undergoes fragmentation to get the two ethenes or two alkenes again. The only difference is the exchange between the substituents and the exchange of carbon positions are also happened as a result of this olefin metathesis. As I discussed earlier, ring closure metathesis, that is, when a diene is used as a starting material, then there is a chance for the compound to make a ring, or a ring closure occurs in this reaction. So a metathesis reaction that forms a ring is called ring closing metathesis, or RCM. Usually, we will choose these ring closure metathesis to synthesize cyclic alkenes having carbon from 5 to 30. So if you want to make a bigger sized cyclic compounds, you can choose this ring closure metathesis. And the main catalyst that we choose for this ring closure metathesis is Grubbs catalyst, especially there will be a metal like tungsten, molybdenum, platinum or ruthenium, etc. So that involves Grubbs catalyst. And usually this type of ring closure metathesis is conducted in dilute solutions. So that two reactive ends, see here, two reactive double bonds are here. So these two reactive ends of the same molecule will have the higher probability of finding each other to make this ring, or to complete the ring closure. So that's why these type of reactions are conducted in dilute solutions. And this type of ring closure, if the two dienes are in the same compound or same molecule, then the ring closure occurs in the same molecule. So these type of metathesis can be referred as intramolecular ring closure metathesis. So the key intermediate for the metallocyclo is the key intermediate of this reaction is a metallocyclobutane, and you can see here the catalytic cycle here. This metallocyclobutane have the capacity to undergo a cycloreversion either towards the product, which is a product with this one, that is an exchanged compound, or in this case a ring closure, and in this case this M is exchanged, that is M from this alkene group is exchanged to this cyclic compound. So either towards that product or towards the starting molecule, this metallocyclobutane can convert this reaction. So when olefins of these substrates are terminal, then the driving force for this ring closure metathesis is the removal of ethene from the reaction mixture, which is also explained in the previous slide. So the result of this ring closure mechanism or ring closure metathesis is the expulsion of a simple ethene from the reaction mixture along with the formation of a cyclic compound. Next is the construction of 4, 5 and 6 membered cyclic compounds. First one is oxetane. Oxetane is a 4-membered cyclic compound with oxygen as a heteroatom in it. So in order to synthesize this 4-membered cyclic compound oxetane, there is a named reaction, Paterno-Bucci reaction is used. So what is that Paterno-Bucci reaction? It is a photochemical 2+2 cycloaddition reaction to form 4-membered oxetane rings from an excited carbonyl compound reacts with the olefin. So basically this oxetane is a product of photochemical reaction of carbonyl compound with an olefin. So that is what known as Paterno-Bucci reaction. Here you will see this is the CO carbonyl group and this is another olefin, and then after the photochemical excitation you will be expecting two compounds with their stereo selectivity, and we will look at that priority order later on. So what will be the mechanism of this Paterno-Bucci reaction? Like I said, there is a carbonyl group, so it will be photo-excited first on photochemical reaction, and two excited states like a singlet and a triplet states will be formed. Once these excited states are formed, either singlet or triplet state may combine to form the cyclic compounds. Especially the singlet state is very short-lived, and they'll combine each other, that like n pi star or pi pi star transitions, and these transitions are rationalized by invoking the diradical intermediates. So once this ring formation, here you can see this double bond is cleaved and this double bond is cleaved, and these radical sites are combined together to form the cyclic compound. So once this cyclic compound is formed, the reverse reaction using the same photochemical light or photons is not possible, since the breaking of this single sigma bond is it takes much energy compared to the double bond. So the reverse reaction is not that possible. So once this carbonyl photoexcitation is completed, then the formed singlet state will be reacting with this alkene to make the cyclic compound oxyetane. Next cyclic compound is cyclobutanes. One easiest method to synthesize cyclobutanes is eno-alkene cycloaddition, which is like a very familiar cycloaddition, like a 2 plus 2 photo cycloaddition. So this type of 2 plus 2 cycloaddition, which follows Woodward-Hoffmann rule, addition reactions are used for producing cyclic compounds like cyclobutane. So usually this reaction involves treating an enone with an alkene to produce a cyclic compound, and the reaction between these enone and alkene is a kind of stepwise reactions, and in each steps it involves diradical intermediates, as you can see in the picture, and these radicals join together to form the final four-membered cyclic compound here. As you see in the mechanism, it is typically similar to the 2 plus 2 photocycloaddition, as I said earlier, and it is proposed to begin with the photoexcitation of enone to a singlet excited state. So initially this carbonyl group or enone functional group will be photoexcited to form an excited singlet state, and then we know that this singlet excited state is having very short lifespan, so it is much easier to convert into a triplet state. So suddenly it will convert into triplet state, and in that excited triplet state it will make an Xe plus state with a ground state alkene, and finally it will give a kind of a triplet diradical, and a spin inversion to that singlet diradical will facilitate the ring closure here. Finally you will get the product cyclobutane. So that's the basic mechanism of enone alkene. Like I said in the beginning, pattern-Ritchie reaction, there you see there is two alkenes where photochemically reacted to form a compound like oxyetane. But in this case here